Shawn LeMons. I was with Mitsubishi for 5.5 years. Currently, I'm with the HVAC installation company as a vice president and a partner, and sort of learning some of the stuff I hadn't had a chance to learn before. Again, sort of reinforcing some of my knowledge base where I didn't feel like I had that much knowledge. But I come from building envelope as well, as a HERS rater, as a PHIUS plus verifier, as a RESNET rater, etc. So 11 different certifications. I've let them all go because frankly, I just didn't want to keep them up, and I just get to use the information and help people out. So that said, we're going to cover, I have probably too many slides, too much information, but that's okay because we can sort of move forward and backward and answer questions. That's really what my goal is, to answer questions that you all have. So I'm going to lay down sort of some thoughts, some basics, some examples of cold climate equipment in Colorado and up in the mountains in particular, some field data, some that I've measured on my own home and some other homes, demonstrating, documenting how much or how little power you're going to need, and then talking about a little bit more specifics on panel upgrades, and then end with some bigger thoughts. So I'm going to start with one of my personal whys. Waste not, want not, right? We could talk about this chart for a year. Not really, but it's from the Energy Information Agency, put together by Lawrence Berkeley National Labs. The United States uses 100 quads of energy every year. What's a quad? Well, a quad is a quadrillion BTUs. A quadrillion BTUs is a gallon of gas being burned every second for 264 years. It's a lot of energy. And the United States uses 100 of those every year, right? So that's 26,000 years worth of gas, 1 second gasoline to run the country for a year. Okay, that's a lot of energy, takes a lot of energy to run the country. Why am I pointing this out? I'm not so much worried about how we're using it. I am, but that's not the point right now. The point is we're wasting most of it. We're wasting 2/3 of it. And I think we can do better. Right? That's kind of my big why. That's what drives, a big piece that drives me. And so I got into heat pumps. I got into building envelope, building science, and now I'm working with heat pumps. And I'm not talking about this kind of heat pump that maybe some folks have had bad experiences with, but rather heat pumps that operate in more familiar ways, like your refrigerator. Right? Your refrigerator is a heat pump that moves heat. It pumps heat out of the box and into your living space, but it makes that box nice and cold. Probably 0 degrees, -2, -4 inside the freezer, just to keep your ice cream cold or what have you. Even the refrigerator part of it, of the box, is probably about 35, 37 degrees, just a little bit above freezing, and it's pumping heat out of that box. The picture in the middle there is zoning, right? We've gotten familiar with cars that have zoning for the passenger side, for the driver's side, for the front, the back, etc. So now we're starting to think about comfort on a zoning basis in our daily lives. And on the right side is a variable speed drill. And I like a variable speed drill better than a single speed drill. And I like a cordless drill better than a corded drill. I'm not saying that those other ones don't have a use, but we're getting more familiar and used to these better technologies. And it's proven by the United States, the American Heating and Refrigeration Institute, whose job it is to track this information, track furnaces, air conditioners, heat pumps, as well as water heaters, etc. and so on. There's a lot of different pieces of equipment that they track national sales of. But the orange line shows heat pumps they've surpassed furnaces over the past few years. Now, there's been a notable downturn in HVAC with a lot of uncertainty in the economy, etc., higher interest rates, what's going to happen, waiting for big rebates to hit, etc. But the point is, there's no going back on the heat pump side. Heat pumps are going to continue to excel way past furnaces, gas-fired. And what does a heat pump do that a furnace can't? It can cool. Right? So eventually, of the roughly 10 million systems a year that are identified in this 2024 estimated number, the heat pump can do both features, can do both functions. And so eventually heat pumps are going to outpace both, not only the furnaces, but the air conditioners as well. So that's starting to show up in how we build buildings. Not only existing buildings and retrofits, but new construction is happening pretty quickly. Left side is residential new construction. Heating fuel is changing towards that electricity, that orange line on top. On the right side of the screen, that is residential new construction for a single unit. Sorry, left side is multifamily, right side is single family. So multifamily has gone electric faster than single family, and single family is soon to catch up. It's a little bit older data, but you see the trajectory that those lines are taking. So we have to start thinking about, as we see heat pumps spread out across the United States and beyond. I mean, the U.S. is slow to adopt the technology, but as it spreads out across the U.S., we have to start to think about the cold areas like Colorado and up in the mountains versus the Front Range versus, say, Glenwood Springs or, Grand Junction or Pueblo or such. So there's different capabilities of what people are calling cold climate heat pumps. The blue line there is really a standard heat pump. That's the one that people refer to when they say, oh, they don't work in our cold climates. They're thinking about older technologies like that blue line. That blue line indicates that dropping off of capability as the temperature drops. Temperatures along the bottom there from 47 degrees on the right hand side and negative 13 on the left. And by the way, if anybody has trouble seeing these, I encourage you. I won't be disturbed if you get up and move closer. It won't feel weird like you're encroaching on me. It's all good. But what I want to point out is that orange line is sort of this next tier of heat pumps. They are cold climate according to definition, but they still have this notable drop off starting at about 17 degrees. We get colder than 17 degrees pretty regularly in the Front Range and definitely up in the mountains. So my position is that that category of equipment, while useful in maybe a little bit warmer climates, is not necessarily the right spec for the Front Range and for the mountains. That red line across the top and down the very left side, that's really the true cold climate heat pump. 100% capable at 5 degrees or thereabouts, rounded numbers. And it does taper off, but it holds its capability at or near our design temperature of about 0 degrees in the Front Range. Whether it's 1 degrees or 5 degrees or -1, we're just talking about similar numbers there. The key is that the systems are capable of doing the work that we need for our homes and our businesses at about 0 degrees, and then they do start to taper off, and we just can add in a little supplemental on top of that. So breaking it down sort of groups a little bit here. On the left-hand side, you've got gas furnaces and AC. I've grayed that out. We're not going to talk about those. The ones in the middle are more those standard heat pumps, traditional heat pumps. And they have some great capabilities and some great efficiencies, just not necessarily for our climate. So on the right-hand side, you're going to see similar performances in terms of SEER and efficiency and what we call COP and these kinds of things. But that you see that third from the bottom line, typical heat efficiency, 200 to 400% efficient. Right? This is where people start to get a little hung up. How can you have something that's more than 100% efficient? Well, I'll ask you, how can you lift something that's heavier than what you can deadlift? If you have a limit of lifting 100 pounds off the ground, how can you personally lift something that's heavier than that? Well, you're going to use a lever. You're going to use a pulley. With the right engineering, you can lift something much heavier than what you would otherwise be able to lift. Right? It's just an engineering problem. And that's really what the heat pumps do. So for every 1 unit of energy they put in, you invest with your utility bill or your solar panels or your battery system. Every unit of energy you invest, you get 2 or 3 or 4 units of energy out of the heat pump to heat or cool your home. So drastically more efficient, getting after that waste of energy that we saw on that first slide. So, another piece of the efficiency is this sort of on and run low and slow over time, rather than an on-off scenario. The on and off, it's not a bad thing, but you start to give up efficiencies. You give up momentum, if you will. It's sort of like slamming on the accelerator and then coasting into a stop or something like that, without actually sort of recovering or benefiting from the momentum of the vehicle very much. The heat pump will charge up that refrigerant, it will run low and slow, and then it'll settle back and it'll maintain. It's kind of like as you accelerate up to freeway speeds, your fuel efficiency is lower. And then as you get to a speed that you're maintaining, your fuel efficiency starts to climb, starts to level out. That's sort of what we're seeing here. These systems want to run continuously over long periods of time. So, and that's where that 40%, up to 40% on the top right corner there. Inverters are just using less energy over time because of the low and slow operation. So, sizing of equipment, right? Left side, the system's too small. You're going to run into challenges with backup heat potentially being needed. We're going to run into durability and comfort issues, because if it's a little bit too small, and some people might be fine turning on a space heater or a fireplace or something, and that's fine, but not everybody wants to do that. Not everybody wants to sort of operate their house. They like that automatic, set it and forget it experience that we're used to in modern life, for better or for worse, right? On the right-hand side, too big. Why not just take a piece of equipment that we know is going to cover the heat load and put it in, and trust that it's going to modulate down, trust that it's going to step down and take care of what we need. And so it might not be quite as efficient all the time, but we know we're covered. Well, you also start to give up a little bit of comfort, because you start to run the risk of that short cycling happening. Short cycling means you expect it to run at a little bit more moderate temperature, but it doesn't. It's gonna stop running, because it isn't infinitely variable from 0 to 100. It's more like 30% capacity up to 100%. So if you're oversizing past that 30%, you're not really getting what you're paying for. You're also potentially shortening the life of the equipment. As efficient, as effective, as long durability, designed as they are, if it's oversized, then you're going to shorten that lifespan, because you're sort of out of spec, if that makes sense. Also, you're just paying for more than what you need. Why would you pay for more than what you need? So, considerations. There's a lot of different ways to do heat pumps. The left side, single zones, 1-to-1. That's one piece of equipment outdoor, like maybe your air conditioning now, and one piece of equipment indoor. That can look like your furnace AC combination, or it can look like the thing on the wall that people have seen when they travel abroad to the Latin Americas or Europe or Asia, etc. Right? These are very, very familiar in other parts of the world. They're less familiar in the United States. We're used to what we're used to, right? So a lot of people go for that ducted system, because that's how our homes are designed and built. So whether it's 1-to-1, or whether it's a multi-zone like in the middle, or whether it's a crazy complex multi-zone on the right-hand side, which I don't necessarily recommend, but it's doable. There's a lot of different ways to do it. That's part of the downside, part of the frustration a lot of people feel, is that, well, I don't really know what I'm getting. How do I pick the pieces that go together properly? It's complex. Contractors feel the same way, by the way. They often will avoid these more complex assemblies, because frankly they just are not that comfortable and not that familiar with them either. They're busy doing what they always do. They're status quo. So left side, block load. This is how you calculate the heat load or the cooling load of the home. Block load looks at the envelope overall. How much heating and cooling needs to go into or be pulled out of that thing that you call your house, right? It's the roof, the walls, the windows, the floors, and everything inside. Block load. The right-hand side is room load. You take the block you load and you chop it up into different rooms, and you have different levels of need for comfort, for heating or cooling and airflow, etc. room by room. Maybe you want a different temperature in different rooms. When I like to sleep a little bit cooler, my wife and I started to get hot when we're sleeping at 70 degrees. We like 68, but we want the bed or the living room at 70 degrees, right? Differences in temperature can be beneficial for how you live. Well, that middle one starts to consider a little bit more capability with the newer technologies. We're taking groups of rooms, calling them a zone, setting them, say, at 68 or 69 degrees, and set it, forget it. And then we're taking the other parts of the home, maybe the living room versus the kitchen or other parts, and maybe we have 1 or 2 zones there. Maybe you need a little bit more cooling in the kitchen area or the office space over in the side of the house where you want to sit and you want to be comfortable or what have you. Maybe you have a party load in your living room, etc. Being able to respond to these temperatures is one of the nice things about modern systems. All considerations, another way to look at it, and here's some examples of ducted and ductless and the different pieces and upsides. I'm going to jump to this one and say this is a townhouse. So we're not necessarily dealing with left side, right side. We're dealing with 2 floors, right? The drawing on the right-hand side is the second floor where you've got bedrooms and closets and smaller spaces and smaller loads and doors that close, right? So you want that ducted system to deliver the right amount of air, the right amount of comfort to those spaces. And by the way, you can add in filtration and humidity management, etc. Right? When you want that fresh air when you sleep to be able to rejuvenate your body, to rest well, etc. To manage carbon dioxide that we give off in a closed room. We don't sleep that well with a lot of carbon dioxide. I'm not talking carbon monoxide. That's the stuff that's really pretty bad for you. But downstairs, you might want a different temperature. You might have a different need of temperature depending on the time of year and what direction the sun is coming in, etc. So a small piece downstairs, a small ducted piece upstairs, 1, maybe 2 systems outside. That's and I'll use this. I don't know if you can see this. I'm going to turn on my pointer here real quick. All right, you can see those 2 right there. Maybe 1 of those, maybe 2 of those outside. Now you potentially get into redundancy in the system. Maybe 1 of those runs very low and slow in the winter to heat from down below and be very efficient, right? Heating from below. And then in the summer, you're just cooling the top, cooling from above, and you're using half the energy to take care of comfort in the house. These are all considerations. My good friend Bill Lucas Brown, I think he's presented to you all in the past, and maybe you know him personally. His home, he's got a 100-plus-year-old home, and he put in a lot of different indoor wall cassettes. It's what worked for him. He had brick walls, etc. It worked out for installation. But that's a lot of different indoor pieces, a lot of different rooms. But what he's doing that's really innovative that I like, and I want to put it up here, is that bottom one that has the red box around it, right down here, that 1 wall cassette he has installed in his crawl space, right? So in the crawl space, he's heating most of the year. So now he has effectively a warm floor. Then that warmth is rising up through the rest of the house. He doesn't have to turn on the other units until about 30 degrees outside. And he doesn't have to, and then those start to run. And the system is a little undersized for what he needs, and that was on purpose. But he adds a space heater, possibly 2 if it gets really, really cold, and that starts at about -5. So that's actually past our design temperature. So he's covered with 1 outdoor, multiple indoors, only 1 of which he uses most of the year. So I'm not saying that this is like a common design that I would recommend for everybody, but it's a novel use, something to think about. So getting into some more extreme examples, these are homes up in the mountains. Both of these happen to be in Fraser, Colorado. It gets pretty cold there. One on the left, I met the gentleman, Joe, and I can't remember his last name, but he came to an event that I spoke at. He said, yeah, I've watched the thing operate at -30. It doesn't give me all my heat, but it gives me very efficient heat, 150%, efficient at -30. And then he adds in some additional heat as he needs to. But it does the rest of the heat the rest of the year. The right-hand side, that was 2 separate systems that were run one-to-one, sort of upstairs, downstairs, and very, very, very efficient systems. They have solar, they have a very good envelope, they have backup systems installed in the house, but they haven't needed them because the system is doing the job, and they're net zero in Fraser for the past couple of years, which is awesome. This system's down near Salida. It's actually Nathrop, and a nice new home. Pretty good envelope, not amazing, but a pretty good envelope, and sort of a north-south arrangement. So both of those outdoor units are connected to sort of half the house, if that makes sense. And the builder, he wasn't even done yet, and it was -22 I want to say this was probably in a February time frame, and he was a little bit nervous about the house, and he went there and it was 68 degrees or so, something like that in the house. He said it was amazing. They have ductless units. They have 5 ductless units around the house. They don't have ductless units in the bathrooms, but they have heated floors, heated tile, right? So about 10% of the square footage of the house is bathroom tile with a little bit of heated mat under the tile. New construction worked out really well. So nice, warm, cozy floors in the bathrooms where you're wet and naked, and then very efficient heating throughout with different temperatures in different spaces. This one is in Snowmass ski area, 11,000 foot, 11.3 elevation. People worry about elevation and how do you do it up there? Well, you just do the math. You just do their D rates. You do the calculations to figure out, well, if we only get 90% of the capabilities at 5,000, we're probably only going to get, well, less than 80% at 10,000 or 11,000. You just do the math. That's oversimplifying, but you get the point. And we opted to not do anything special to the unit other than lift it up 5 feet off the ground. You can see the gentleman, it's right there in the bottom right-hand corner of the photo right here, and he's reaching up to get to that unit. But on the left side, you can see it's basically at the snow level. So we allowed for a lot of snow at the top of Snowmass, and the only time that it didn't do the job was when they got 5.5 feet of snow in 9 days. And they didn't clear the snow away. It's not the amount of snow per se. It was the fact that the snow got caked in. They didn't maintain it. They didn't watch it. So that's an extreme amount of snow. And that could happen in the foothills or wherever you're at, but unlikely, right? So all you really have to consider is just make sure that the thing has airflow and the snow is moved away and managed. Plan for it. This system is in Ontonagon, Michigan. I put it up here because it's a great little video, and we'll provide the PDF for you all to look at. And these links that are down in the bottom, all these links, they should be live. I hope that they can come through on the PDF, but it's kind of a fun video. This is a retirement community. They were all electric. They were having very, very high utility bills, and they considered going on to gas because of the lower cost of fuels. And the utility company said, hold on a second, let's think about this. And the utility company worked with Mitsubishi in that area and contractor in that area, did the math, figured it out, put in heat pumps. They avoided putting in gas. They avoided putting in, I think it's, 60 units. A 60-unit development retrofit with gas lines potentially entirely avoided. Right? So yes, they have heat pumps doing it. Yes, they still have electric resistance baseboards in there, but they basically don't have to turn those 100% efficient systems on because now they're running at 150, 250, 350% efficient with the heat pumps. It's a pretty great story. So we need to, as you can see, we're starting to drill down in the details, right? Any questions so far? I want to make sure we're getting everybody. Yeah. Great question. Different manufacturers specialize in different equipment. What you're really talking about is sort of a water source heat pump. I I don't work with water source, so I apologize. I'm not going to be able to speak to that in great detail. I know a little bit about them, but Mitsubishi does not have, and I don't work for Mitsubishi anymore, so I just know the product. That's why I talk about it. Most manufacturers of this type do not have necessarily a water source on a residential, for residential equipment, but I think we're going to be seeing that change. Go ahead. No, so water source and geothermal, etc. I talk about ground source per se. Like, to me, geothermal is what Iceland does. They're 5,000-foot wells and come back as steam, and that's geothermal, right? So what I was wondering about is how, what I've been wondering about is how these different brands are going to sort of tackle this new opportunity. So yeah, I would look at, give it a little time. We'll see what the market, how the market develops, because there's stuff outside the U.S. that's coming to the U.S. soon. Does that answer your question a little bit? Any others? Any other folks? Yep, keep going. All right. That's right. Sorry, Martin, you wanted to keep questions to the end. We're rolling. All right, so double checking the specs. These two pieces of equipment look identical. They have a very close match on model number, and yet they perform very differently at cold temperatures. When you look down at this end of the scale over here, so this is, these numbers are really small, I apologize. This is 47 degrees, this is 17 degrees, and this is 5 degrees. So at 47 degrees, they look great. At 17 degrees, this lower one looks less great. That red wedge is resistance heat that you're going to have to make up. That's heat you have to fill in the gap with. And probably electric resistance, and probably more expensive. And as it drops down to 5 degrees and lower, that continues to slope down, eventually to the point where this lower system is going to turn off. It will shut off at -8. That's the cutout temperature on this particular piece. Now, it's not a bad system, and there's many manufacturers that have this scenario in their product mix. It's not that those other ones are bad. It's just that they're not engineered for our climate. Even though they're qualified for the NEEP cold climate list, you have to really double check your specs and make sure you're looking for that 100% capable at 5 degrees, as opposed to, say, the 70% capable at 5 degrees. If you want to run on solar, if you want to run on batteries, if you want to be efficient, because any resistance heat, or if you want to get off of natural gas and you're doing all electric, that electricity is going to compromise your efficiency. It's going to cost you more. You're buying bigger systems to make up for it. So here's a different way to look at that. Left side is down on the bottom you can see sort of a picture, right? 1 outdoor unit, 2 air handlers. So it's a multi-zone. 1 outdoor, 2 indoors. Yes, this is doable. It sounds strange, but it's part of how these systems can work. On the right-hand side is 2 separate systems just duplicated. These are 2, technically 3-ton systems that are put on. Now, if you look at the COP, this efficiency, that's a measure of efficiency. It's energy invested, energy output over energy input. Sorry for the technical stuff, but we're going to get into this, a little bit more of this in a couple minutes. But the efficiency ratio is higher, 2.48 at 5 degrees. Well, that's a pretty efficient system at 5 degrees. This one is only 1.9, so 190% efficient at 5 degrees. This one is 248% efficient at 5 degrees. Well, that sounds pretty good. Why don't we go with that? Yes, but as the temperature drops, the capacity drops. Right? And at -4, the system is off. So you have to put in an 18 kW heat strip or something similar to heat the house to make up the difference for when that system diminishes or is off. And that's an entirely second system, right? It's a backup system, which is fine. It's not a bad strategy. It's just a consideration that you have to grapple with when you're paying to size systems, paying for equipment, and then powering it with your solar, your batteries, a generator, however you want to do sort of your resilient solution. On the left-hand side, this red line right here, this single outdoor and 2 air handlers is able to maintain 100% at 5 and about 80%, I don't know if I have it in there, yeah, let's call it about 80% at -13. It's going to continue to diminish slowly, but you can see this little 3 kW strip right here that's supplemental heat instead of 18 kW of backup heat. It's a big difference, and it's so big that it's going to take 190 amps of breakers on your panel to run the system on the right. And it only takes a third of that, 65 amps to run of total breakers to run the system that is more efficient when it's colder. And to me, that's a better system for our climate. And there are multiple manufacturers that provide that level of capability. So I'm going to skip over this one. This is pretty big. I'm not going to quite skip. I'm going to say that these are specifications. These are national programs that determine these types of specs. And what I want to point out is these little, I put in the clocks, right? There's an alarm clock in here. Wait and see for new equipment coming out that, maybe it's going to be better in some ways. Maybe there's systems out there right now that are going to be great. But we're going to see pretty significant differences as well as significant cost increases on equipment in the next couple of years. So you have to balance time, money, efficiency, environmental impact. Like, what is your personal choice? But know that there's some pretty different stuff coming. So we're going to dig in a little bit deeper. I'm going to talk about the refrigeration cycle for a minute. Anybody excited about this? All right, great. We got 2 hands. We got three hands. What I want to point out here is really thinking in terms of phase change, right? You think about ice. It's water changing in solid form. That ice melts and it cools things off for us. It becomes water. And then that water boils and it turns into steam. And we can do things at these phase changes. We can put that phase change to work for us. And by the way, that's sort of how we built our civilization, is on steam, right? Going back 150 years or more. I actually can't remember when steam came on, but it was a pretty big deal. And it's this gigantic block of hidden heat that we're really benefiting from with steam. Right? There's no change in temperature as it changes from water to steam per se. But there's 970 times as much energy packed into that phase change. And whether or not you're putting the energy in or taking it out, there's this exponential hidden heat that's available to us. And that's really what's going on with the refrigerant cycle. This is why it's sort of magic, but not really. All the heat pump is doing is managing temperature and pressure of the refrigerant, right? And so it's managing and it's balancing that around the phase change from liquid to vapor of the refrigerant. So a little more pressure, a little bit higher temperature of phase change, a little less pressure, a little bit lower temperature of phase change, etc. All it's really doing is balancing that out at every second as the system runs throughout the year. And so it's going to capture heat from outside. And that's where that refrigerant is going to boil off, right? It's not boil off. It's changing from liquid to vapor. It's boiling outside as it captures the outdoor heat into that large block of hidden heat and a large capability of hidden heat. It then moves it inside the house. It raises it up in temperature some with the compressor. It compresses it and adds a little bit more heat in. And then it delivers that extra hidden heat into the house. And that's roughly the refrigerant cycle. As it comes back through, the pressure drops. So we have a pressure increase and a pressure drop across that cycle. So as it compresses, it raises temperature. As the pressure drops or depressurizes, and it drops below that boiling point, below that outdoor temperature. And when the outdoor temperature is warmer than the refrigerant at the right pressure, it can boil off again. Refrigerants boil at about, I don't know, negative 60 degrees Fahrenheit or something like that. So we're just managing it. So I'm going to use that same picture, and I'm going to talk about a little bit of heat pump math. I'm going to jump ahead a little bit. I'm going to skip ahead a little bit. So I'm going to go one further. So this is, this is where I was like, that's probably too much. We'll see how it goes. And ask questions, please. So what we have here is the refrigerant cycle. We've got 9,000 BTUs. We're getting towards 18,000 BTUs. Arbitrary 1.5 ton size, don't worry about that. Just know that we're targeting 18,000 BTUs. And we're operating at about 200% efficient. So there's 9,000 BTUs absorbed from the air outside, and we're investing 9,000 BTUs in the compressor. That's what we're paying for on our utility bill or from our solar panels or from our batteries or what have you. So we've got this 1-to-1 ratio to create 18,000 BTUs of heat. Okay, well that's at 5 degrees outdoor temperature. That's pretty good, right? We're 200% efficient at 5 degrees. Well, here's how it basically boils down, the math, right? 18,000 divided by 9,000 input. 18,000 output divided by 9,000 input is a COP of 2 or 200%. Here's your watts if you really want to dig into that. And that's great. That's a piece of equipment that's 100% efficient at, 100% capacity at 5 degrees, operating at 200% efficient. But what happens when we look at one of those 70% efficient systems that is more efficient? Well, we're operating at a COP of 2.5. That's 250% efficient at 5 degrees. Is that better? I don't know. Let's look. 7,600 BTUs absorbed, 5,000 invested. We're only getting 12,006 out of this scenario. So we're short. We don't have enough heat to do the work that we need at 5 degrees. We were targeting 18,000. We're only getting 12,600 out of this scenario. Yes, it's more efficient, but we're not getting enough, because what they're doing is they're dialing back how much energy goes into the compressor. They're pulling back and saying, I'm not going to invest as much. Yes, I'm getting a pretty good absorption rate. I'm getting pretty good efficiency. I just am not investing as much, so I'm not getting the overall as much out of it. So what do we have to do? We have to add in additional heat. We have to make up for that 30%, right? So maybe that's electric supplemental heat, like a strip heater, whatever you want to add in, the space heater, etc. But now we have to account for that extra energy, right? And so when we add this up, the 5,000 from the compressor plus another 5,400 from the supplemental, and we're hitting 18,000, but our efficiency is 170% instead of 250% that we bought and paid for from the contractor that said, oh yeah, 70% efficient heat pump, it's going to be great. We'll just put on this extra thing just in case. Well, just in case it's happening at 5 degrees, which is actually warmer than our design temperature, and we see that temperature, not all the time, all the winter, but we're going to see it a lot. And you're going to be paying a lot more. You're not really getting what you're paying for, in my opinion. So, let's look at, I'm going to skip that. I'll do this one. So this one is Denver. This is a 4-ton heat pump. 4 tons is 48,000 BTUs and up, nominal number. It's got 2 duct systems, very similar like we saw before. 200 amp span panel, which is where I pulled this graphic from. It's not my house, it's a friend of mine. And on December 22nd of 2022, anybody remember that a couple days before Christmas 2 years ago? Really cold. Yeah. So this house saw -18, and the design temperature is 0 degrees. So this system is going to have to work 25% harder to heat the house, keep the house at 70 degrees in this condition. It's 3,700 square foot home. The heat load is 46,000 BTUs, right? So this 0 degrees and 46,000 BTUs load. That's sort of the design. That's what the system was designed to take care of. And they said, well, we don't need backup heat. We're okay. We're going to be able to hit this without backup heat. Okay. Along comes the cold. What happens? Well, the homeowner stays happy. It was a little chillier, but they were very pleased, right? And the cold bathroom that was always cold on winter days like this was actually now warm because of that set it, forget it, long run times, continuous airflow, etc. Here's the key right here. This is what you all came for. And sorry for the slow buildup, and I hope it's worth it. But the point is, this piece of equipment is designed to take for 42 amp or really a 45 amp circuit or a 50 amp circuit, whatever. But it's rated for 42 amps of ampacity. It's 10 kWs. On this 25% beyond design temperature day, it stayed below 25 amps. It stayed below 6 kW. Not 10 kW, but 6 kW for that day. It heated the house, and it actually averaged, throughout the day, it actually averaged slightly lower than that. So this thing is cranking most of the day. It's operating at like 90% capacity for the entire day. And this is the weather data over here. Here's our low of -18. And it wasn't that cold all day, of course. It got to a high of -4, right? So there's averages involved there. But we're still operating 200% efficient. I would say that's pretty good. And it's definitely better than what the specs say. The specs would say you're pumping 10 kW into this thing at 0 degrees. And we're beating that, right? Let's go to another house in the summer. So a little setup on this. It's 97 degrees outside. It's afternoon, 3 p.m. Design temperature is 95. I forgot to put in here that the temperature is okay. I'm sorry. It's 97 degrees outside. The design temperature was 95, so a couple degrees past design. 20,000 BTU load is what the calculations say. At basically just before 3 p.m., the system turns on. So here we are. We're heading for peak rates from Excel. Thank you very much. And it runs for 14 minutes at 1.8 kW, 1,800 kilowatt hour or kilowatts for 15 minutes. And then it steps back, and then it runs at 1.3 kW for an hour and a half. It's because it was off before that. It steps up, sort of cools the system, cools off the ductwork, cools the refrigerant inside, and then it settles back and runs for 90 minutes at a little bit lower rate. And over an hour and a half, peak rates on Excel's system, this undersized PV system, because of just limitations on the roof and trees and all that stuff, the undersized PV system is still big enough to cover the cooling load and a little bit of operational stuff, the fridge, maybe something in pumps or whatever going on. And so we're still net positive production for that time frame to the tune of 200 watt hours, right? So we're effectively invisible to the grid. We're not paying those high rates, right? To me, that's a win. It's not 100% PV rated for the biggest days and everything you need all year long. It's not covering your 100% of your bill all year long, but it is big enough to avoid the peak rates in the summer and keep you cool without having to curtail AC and be uncomfortable. Here's the kicker. How much power do you need? It's rated for 24 amps, 30 amp circuit, rated for 24 amps ampacity. It's 5 kW. It stayed below 8 amps, and it averaged under 6 amps for that hour and a half. So what's going on here? We're past the design conditions. We sized the system for the design conditions, but we're operating well below those. What's really happening? Any guesses? This is for the, well, sorry, Martin, I'm holding the questions to the end. We'll come back to it. What I really love is that we're still operating at 320% efficient. And here's the other big question mark. 1,600 BTUs on a house that's designed at a heat load calculation, cooling load calculation of 20,000. So there's this disparity. We can get into that in the Q&A. So that's some field data, right, on operation of the heat pumps from one perspective. And so just some goals. Actually, do you want to know about how to sort of plan around heat pumps and where to locate them? We can get to that later maybe. Is that all right? We'll keep rolling. All right. We'll come back to those. Defrost cycle. It's kind of fun. We'll come back to that as well. That's sort of outdoor unit location. Here's another fun part. And thank you very much to Jim Myers from Sweep, who is amazing. And he pointed this out to me a year and a half, actually 2 years ago. He said, so Shawn, there's this section of the National Electric Code that allows for to data monitor and size below the rules. And it's code compliant, right? Cool. Really, we're looking at this exception. It's section NEC 220.87, and here's the exception. The exception says, record energy use on the house for 30 days, 15-minute increments, and include your big loads. Prove it, and we'll allow it. That's basically what it says. Cool. So I use an Emporia monitor on my house, and we actually install those with our business as well because I think it's the best monitor for the data, the robustness. The displays are not great. They're getting better, but anyway. It's the one I used. And here's a layout of my breaker panel. It's a 100 amp panel, and on that panel I've got an oversized range breaker. I've got all the regular stuff around the house. I've got a whole home surge protector in this undersized panel. And that's really related to the grid and solar and such. I've got solar down here. I've got my dryer here. Notice what's next to my dryer. EV and dryer on the same circuit, right? So it's a smart switch because I don't run my dryer all week or at 3 o'clock in the morning, right? So 95% of the time I can charge my EV no problem. And if you need to run the dryer, it's a smart switch. So it just gives priority to the dryer. So the heat pump is here, and that's the setup of my breakers. So I monitored my system. I pulled down data for 13 months worth of data. The requirement per NEC is 30 days, 1 month. I pulled down 13 months. And I said, how's my system doing? How's my house doing? How much am I using? Well, after all that, the absolute worst 15 minutes was under 50 amps on a 100 amp panel with a heat pump, all electric. To be fair, I have a water heater that's on gas, but that's why I did all this. I'm like, can I actually put in a water heater on this, on another 30 amp circuit? EV, I drive 25,000 miles a year on my EV, so I charge a lot on a 30 amp circuit, by the way. Not a 40 amp, not a 50 amp, not a 60 amp, 60 amp, whatever. Why would you do that? Why would you put that strain on the grid? It's a terrible idea. Anyway, so I'm running my entire life where we don't compromise in any way. We're very comfortable and on a 100 amp panel, and I'm using half of the 100 amp panel. Proof for a year, over a year's worth of data. There's a house that I didn't show you earlier on in the slides. I skipped over it. It's up in Leadville. Everybody knows where Leadville is at? Yeah, it's pretty cold, right? Higher elevation, less efficient, heat pumps. It's a pretty good house, to be fair. They were required to put in a 200 amp panel because it's relatively new construction. It's 3 years old now. And on their 300 amp panel, and to be fair, they're not there all the time, but when they're there, they're fully there. Like there's people and stuff, and they're heating and they're going skiing, they're doing all the things. Their worst 15 minutes was 42 amps. 42 amps out of 200 that was required by code. So, how much do you need? Well, these folks out in California basically surveyed a bunch of households, statistical analysis. They said 98% of the houses in California do not need panel upgrades. Because is enough 100 amp enough power? Yes. What you're looking at here is this blue curve is the sample data of what those homes are using, right? Here's the peak. And 98% of them, roughly down here or something like that, they're under 90 amps. 86% of them are under 50 amps. And just under half of them are under 30 amps. And most of those homes are houses with 200 amp panels. Plenty of capacity. Now, I'm not saying that the California grid doesn't have its problems, but the breaker panels are not the problem. So, you got to measure it to improve it, right? Lord Kelvin, anybody knew Lord Kelvin? Kelvin scale, yeah. It's fun numbers. Anyway, what he's talking about is that, hey, if we want to get to where we need to be, let's measure it. I'm not saying to anybody, I'm not saying to the electricians, the engineers, the HVAC, the builders, the code officials, I'm not saying that they have to do these things because I said so. I'm saying decide for yourself. Go and measure it. Check it. You did a bunch of designs on your electrical load calculations? Fine. Put an energy monitor on it, on 2 of them, 3 of them, 5 of them. I'll bet you a nice dinner that it's not going to be a problem. But let's find out. I put in some slides about the Marshall Fire. I thought it would be interesting. I'm going to skip ahead a little bit and just say that, from an all-electric perspective, that was as tragic as that entire scenario was, and I remember the day, I'm sure we all do, there's 11% of the homes going back in that are all electric, which are basically the passive house, which is about 1%, which seems small, but it's actually a large percentage, a large grouping of passive homes. And then Energy Star Next Gen, which is an electrical requirement, electrical spec basically for new construction. So a little over 11% going back in based on the building permits. Thought that would be interesting to share. Here's a quick study of 4 homes in, 3 new homes in Marshall Fire and 1 older home as a baseline comparison that has a bunch of efficiency upgrades to an older home, etc. All of, pretty large homes, 4,000, 4,500, 3,300 square feet. What we're looking at here are kilowatt hours on the utility bills, right, for November of 23. Let's see, 8 days, 12 days. I have to admit I stole this from somebody else, this slide from somebody else, in the way that I didn't fully digest it. But what I do know, because I did help gather some of this data, is that these numbers, this is kilowatt hours for a heat pump house, all electric, with solar, but they've got pretty big electric backup, right? And that's really where that electric backup is showing up on the utility bills at these low temperatures, right? So 8 days, 12 days, 18 days, average temperatures, but lower operating condition or operating temperatures, lower lows, I should say. So the cold climate, true cold climate, 100% capable cold climate heat pump, way outperformed by a third or even better of what the non-cold climate plus electric backup, the 70% houses versus the 100% houses. Sorry for the complexity of that slide, but thought it'd be interesting to share. So if you're considering which way to go, again, I'm not saying that those sort of intermediate cold climate heat pumps, the 70%, are bad pieces of equipment. They're not. They can be very efficient pieces of equipment, especially on the cooling side. But what's your backup? If you have an existing house and you have a gas tap and you're considering which way to go, it's not a terrible idea to drastically reduce your gas usage, but still keep it when you really need it. To me, that's okay. I'll take 95% gas reduction all day long, every day, right? Now, if you want to go that extra step and close it and shut off that gas cap, right? You want to cap that thing, and you want to go all electric and heat your house, you're going to want the 100% capacity heat pump because it can handle it. Just be designed properly, have a little bit of additional heat when you need it, right? Maybe it's I'm going to get the wrong term here, but if you're banking kilowatt hours with Excel, this is where you spend those extra kilowatt hours in January, right? Anyway, and also get through a year's worth of utility bills and then go on, once you're sort of normalized for the full year of utility bills from Excel, then go on average billing, because your average billing is going to sort of level out your utility bill from the high in January to the very low on the swing seasons to the really very moderate or modest in the summer, particularly if you have solar. So something to think about. You asked about utility bill, or incentives earlier. There's a little bit about incentives here. Rewiring America has an excellent rebate finder, rebate calculator. You type in a little bit of information, zip code. You can put in your annual income if you want to. It helps with some of the qualifications, helps filter down some of the choices. And a little bit of information, they really pull up a good bit of information on rebate and incentive qualifications. And Love Electric is a Colorado group that I think is doing great work, and they help people understand in Colorado, understand all these choices around heat pumps, space heating, water heating, etc. And they have some rebates information on there as well. But you can see this, excuse me, you can see this non-cold climate. That's the standard heat pump. The cold climate heat pumps, they both, whether it's 70% or 100%, they both qualify in this column right here. So it doesn't really matter. You just got to think about how much extra system do you need, and do you want to get off of gas potentially. And then heat pump water heaters, some good numbers there as well. And that can be, I mean, questions later. Sorry, Martin. I'm just reminding myself. We'll come back to that. Love them or hate them, Xcel Energy is moving, I think, more progressively than many utilities towards this carbon-free electric scenario, and they've surpassed this 50%. They're on, actually, they're ahead of target. I believe they're going to be better than planned when it comes to the end of the decade. Again, I don't know. I know folks in Xcel, but I'm not a policy guy, so I don't want to get into the big debates about Xcel. And they are the lion's share of ratepayers in Colorado, and all of these 6 utilities have some pretty significant goals towards zero greenhouse, or towards greenhouse gas reductions, 80%, 90% by the end of the decade, etc. Okay, gotcha. There's a note on here to talk about Emporia. We'll come back to that in a moment. This came out from Rewiring America a year and a half ago, 2 years ago. It's pretty cool to see, looking at these green bars right down here along the bottom. Those green bars are electricity in terms of seasonally adjusted price difference. So how volatile is your cost of energy? electricity is drastically less volatile. Yes, it's been going up, but not nearly as much as the other sources of energy. And this is sort of this amalgamated slide here. The pink is, this is global liquid natural gas, so compressed natural gas. The pink is how much natural gas Asia is importing. And the blue, importing. The blue is Europe. There's some other parts of the world, etc. Down here, the black is the U.S. So I'm just identifying sort of a scale of how much other parts of the world are interested in compressed natural gas, because compressed natural gas can go in a boat and we can import it, we can export it. You can't do that with electricity. Electricity comes from, on average, I think it's about 10 miles away from your house, on average across the United States. It's a domestic energy resource. It's not an import-export global commodity. Thus, when you look at what happened in, what Putin did to the energy markets, right, when he invaded Ukraine, etc., these crazy spikes in Asia and Europe, they're using more natural gas and they're paying more for it, and the United States is exporting it out to them on big boats. And so maybe that's not the worst thing for us per se, but that does increase the volatility of our natural gas prices. So maybe that's good fodder for you all to go out there and talk about the upsides of electricity. Let's skip that one. I want to sort of, how are we doing on time, Martin? 10 minutes? Okay. I'm almost there. Thank you. So 1935 to 1949, 14 years, we took rural farms from non-electrified to electrified, right? We went from 10% farms having electricity to 70% farms having electricity in 14 years. That's a lot of work. And we did it, and a lot of those grids are still in place now, but what was something else that we did during that time frame? World War II. That's a lot of work too, right? We did all of this in 14 years. We defended the country. We helped the world rise up through World War II, and we got all this done. I think that we can do this work again, potentially. Now, fast forward the next 45 years, from 1950 to 1995. We 10x'd the grid. Right? Some people are talking about, well, how much bigger does the U.S. grid have to get in order to electrify, in order to handle these, EVs and heat pumps and all the stuff that we're doing? Maybe it's 30% larger. Maybe it's 50. Maybe it's doubling the grid. Well, if we 10x'd it in 45 years, I think we can potentially double it in the next 10. Right? I think we'll be okay. We can get this done. So with that, I appreciate your time. Thank you.
All right, thanks. That was a really great presentation. And this is a field I know inside and out.
Great.
I'm an electrician, been a teacher most of my life, electrical. I retired as chief electrical inspector at Berkeley National Laboratory, where they invented most of this stuff.
Nice.
So, it's very good. One thing I marked is on your panel upgrades. Mm-hmm. If you're doing a new house, I wouldn't quibble about going to a 200 amp panel because the price difference isn't that great, and you want a lot of breaker spaces. If you're going to get a lot of breaker spaces in a 100 amp panel, mm-hmm. you're going to get something that's more special order, and you might end up spending just as much anyway.
Yeah.
So, but on an existing house, if you can keep the old guts and put in new interiors, more breaker spaces, that's great if you get out a sub panel. A lot of times when you're doing solar, EVs, heat pump, all stuff, you're adding more circuits. You might have a less total load, but you're adding more circuit breakers. And some of these old 100 amp panels are pretty light on that. So that is a factor where you might have to do something rather than nothing. But yeah, otherwise it's I know, like, I think the real serious problem is from an environmental issue is that people look at getting a backup gasoline generator
Right.
and they grossly oversize it.
Right.
And that's a real problem.
Right. Yep.
Yeah, good
and-
question. And I think you're going to bring up sub panels
Yeah,
as
and then
a
we'll
solution.
segue into the Emporia discussion here. So this is a little sort of, I just worked this up. It's not a true electrical load calc, but you get an idea of how my panel's laid out. I've got 24 spots on this mid-90s GE breaker panel, right? I actually have a spare in here, right? For all the stuff I'm doing, 1,700 square foot house, it's on the smaller side, right? It's smaller than average home, but I can easily take this 2-inch breaker and make it a 1-inch breaker, right? But it's still a GE breaker in a GE panel. It fits, everything lines up. I'm touching both sides of the phasing, etc. And the reality is, if you want to jump ahead in my range right here, where's my my stove? Can't quite identify which one's my stove. Maybe it's over here, but it almost never runs that high. It's rated for 40 amps. It barely touches 20.
Actually, what is the Emporia?
Emporia is so the picture on the left here is the Emporia Energy Monitor version 2, the View 2. The big box in the middle here is about the size of a deck of cards. Each of these little items go around one of your breakers, whichever one you want to monitor. I monitor all my 220 breakers, my bigger stuff, and some of my smaller stuff. I'm not going to monitor my garbage disposal, for example. I don't really care, but I am monitoring the kitchen circuits, right? A left side, right side, etc. And so these mains measure the power into the box, and these CTs, I can't remember what CT stands for. You can probably tell me. Current transformer. So each of these is a current transformer. It's sensing how much power passes through each of the circuits. It does the math. It generates a display. Those are some of the displays that I showed you earlier, where you could see minutes or hours. And it also generates a data set that you can output, and then I started to manipulate it in Excel, in spreadsheets. And I basically deduced that after all of that, under 50 amps, my worst 15 minutes. But here's just as important point. Only 7 out of 35,000 15-minute periods over 13 months were within 90% of that. Only 7 were within 90% of that peak. And only 3% were within 50% of that peak. Right? This is an exponential curve that is working to our advantage. And this, I believe, is why we're not going to burn down the houses.
Okay. You, on that one example, I believe you mentioned the SNAP panel.
Span panel, yep.
Yeah. Does that work out, or you don't have it on your house, so it was just on that one example?
Well, it's funny that you asked that. I was going to do a span panel, and I decided to back off and say, you know what, I'm going to sort of prove the harder path. And that's what I decided to do on purpose. I think the span panel is a great technology. I think those types of technologies coming out are very exciting because it's not just a smart breaker. There's other things that it can do. It can provide information. It can provide resilience. It doesn't, it can turn things off as you get sort of indications that you need to manage power a little bit more. Maybe you just want to manage costs. There's a lot of things that you can do with the span panel, and they come in 100 amp. They have a 100 amp version of it and a 200 amp version, but you can easily do 100 amp plus power 200 amp breaker with power monitoring and the load shedding that span does. And you can qualify you can get out of having to go to 300 amp service or 400 amp service. It's a pretty big impact.
And then the monitoring system that you have now that gives you amps and kilowatts, or the one you were talking about?
You can choose the unit that you're watching.
I have the Sense monitor, and I really like it because I can track every little device in the house. But
yep.
And then the other question, when you mentioned a heat pump water heater, did you look at the 110 volt heat pump water heaters? They seem to be getting pretty popular. And there's
Yeah,
a
I'm
big
on the
study in
fence.
California with like 100 different
Yeah.
heat pump, 120 volt water heaters. That's pretty successful.
I think it's a great product, the Ream, and there's I think 4 different brands that have a 120 volt version, and I think they're going to be good products for the right application. And I'm on the fence personally of whether or not I just go with because I have the space. I proved that I have the space, and I can get it done. But do I really want to run that extra circuit? I don't know. We'll see.
So I also had a follow up on the span panel. I had talked to a solar installer, and they said they didn't want to do a span panel because they were, worried about their guarantees and, that it being somewhat new technology. So I was just curious if you had any information on that, whether, it's something that could hold out over the long run. And then the other question, well, not question, is I was interested in the location of the outdoor unit that you skipped over some of those slides on. So.
Yep.
Thanks.
Yep. Where is it? Okay. I don't have a crystal ball. I think it's a good company. I think they're well funded. I think that they have some great technology, and they have some technology under the hood it's built in already. They're just not releasing it. So it's going to be able to do more when they are ready to release the tech. It's sort of like, again, well, love it or hate it. I'm a Tesla driver. There's more capabilities on that vehicle than I currently use, and I can buy into it when I want to. So I'm excited to see where it goes. Sure. So a couple key points with heat pumps outside: avoid the snow line, the drip line, right at where the roof comes down and the water drips. You don't want that water dripping on the heat pump and then refreezing. You're gonna throw it off in a number of different ways, and it's just avoid it. It's okay if the drip line extends past the heat pump. So if the drip line was right, 6 inches right in front of this, or a foot right in front, I'm okay with that. But just know that you might have some dripping water on the fans and can start to create some imbalance on that fan. You want to avoid that. Defrost. There's water that drips out of the outdoor units in the winter. It's just how heat pumps work. And as it drips out, it refreezes. So potentially, you could have an ice rink on a walkway. You don't want that. You want to avoid that, right? So stay away from the walkways. Stay away. If a lot of people put down pads, they put down these concrete pads or like these faux concrete pads. I personally like pavers. I like to see stands that lift them up out of the snow, have enough space for any ice or whatever buildup, and the feet are on pavers that are tamped down into place, and that way when the water drips down, it goes to the ground and it just goes away. The water doesn't stay there long term. Interesting question. The short answer is on this big one right down here, something like that size, you could get, I want to say, 3 gallons, up to about 3 gallons for a very heavy, very wet, very snowy day. So we're talking upwards of an inch of like really thick snow caking on that coil, and then going through defrost. You could pick up upwards of 3 gallons on that. Now, that's almost never going to be the case, but if you're on the shady side, I'll go to this one here. If you're on try to get the thing in some sun so that the sun manages and reduces that buildup over a cold week or a cold month or what have you. It can really build up if you're not careful, if you're not thoughtful about where it's located at. But you know what it looks like, right? The snow shadow, right, where your fence is, the neighbor's house or the trees or whatever. Wherever that snow shadow is in the winter, try to keep the outdoor unit out of the snow shadow. And you'll be actually probably performing better than spec, because now the sun helps create microclimates around this space, and it does free defrosting for you, etc. There's no sun in the negative 40 degree gigantic freezers where these things are tested. So if you've got free sun, you're going to outperform. maybe you've got trees around and it helps, but I'd rather pay, and this isn't the right number, but it's something like this. I'd rather pay a 3% premium in the summer and save 10% in the winter. Something like that. Yeah, so the question was about noise levels. Noise, I think you would be surprised how quiet these are. They're not silent. They are mechanical devices. They make some noise, and now you're adding some noise to the outside of the house in the winter when you probably didn't have that before. But they're nowhere, and I'll take any attestments that from folks in the audience, but they're probably nowhere close to what you would think of as an air conditioner. Air conditioners, you know, have that heavy hit, that vibrating, whining sound. It's nothing like that. You'll get some different sounds. I'm going to go back to the defrost. These are defrost cycles going on. And so this little ramp up right here in the power, this little peak, it's ramping the fans up to high speed. It doesn't show up much on the power side, but you're going to get sort of this 1 to 2 to 3 minute sort of 90 seconds of like higher fan noise once an hour, maybe. That's what mine does. If you're really cold and really snowy and in a shady spot, you might see it every 45 minutes or something like that. But depends. It sounds like sort of a refrigerator outside most of the time.
Shawn,
Sorry.
question. You talk a lot about monitoring energy in existing homes, but if we are planning a new home, how do we convince the design that we can stay below 200 amps or 100 amps?
Yeah.
How do we do that?
Well, I mean, I'm happy to discuss more about sort of what the rules and regs are. And there's a gal that co-presented with me and Jim Myers at the code officials annual trainings, and she does a very thorough job going through the current electric code and identifies exactly how you can still do a modern build today with a 100 amp panel. So it's doable. You have to pay attention to details. You don't go in and put in a lot more breakers. Like we simply do not need 20 amp breakers for bedrooms, let alone per bedroom, because that's a lot of power. And Energy Star, as a national program, is drawing down the power of devices, of lighting, all sorts of stuff going on. So, in fact, the NEC is stepping away from what used to be 3 kVA per square foot down to 2. They're literally knocking off a third of the base power, if you will, in the calculations. And they're starting to recognize this. So it's a matter of having the person doing your electrical load calculations pay attention to the details and not overspec.
I have a question about timing. I would imagine typically most people turn the heat down during the night and then heat it up, let's say from whatever 62 to 68. Mm-hmm. What is the time frame? How long does it take if you are all electric, to get it, from low to top?
And should you?
Yeah.
Yeah, you mentioned set and forget as the best practice. So if you could speak to that.
Sure. I'll use this as a background. This is where it starts to become really dependent on the equipment you choose, right? The capabilities. So from vehicle to vehicle, you could have very different performance from stoplight to 60 miles an hour, right? How does it feel? How does it run? How smooth it is? How efficient is it? And that's where the guts of the technology really start to show up. How capable is it to get you where you want to be as reasonably quickly as you choose to be? There are settings as well. There's sort of eco settings on a lot of different these things. I will say that we've been programmed by utility companies and just efficiency advisors for decades to set back your thermostat. Oh, well, if you go to work, set it back, you know, what is it, 1% savings per degree per year, or something like that, something along those lines. That setback is what the technology is doing automatically now for you. It's modulating back. It's saying, oh, you want comfort now in the next 5 minutes? I can give you that to you. But then I'm going to settle back and I'm going to maintain. Right? That's sort of what's going on here. And I'm not it's not ramping all the way up. It's only ramping up to identify, oh, you're asking for 2 degrees. I can give you 2 degrees worth of power. But that's sort of summer, winter stuff. In my house, I do set back. I set back at night because we have one central ducted system in our house and we like to sleep a little cooler. I'll set back from 70 to 68. And I won't see any energy use from 11 p.m. to 1 or 2 or 3 o'clock in the morning. And then it sort of maintains at 68. And then at 6 a.m., I go from 68 to 69 degrees, 1 degree. So it's a smooth sort of ramping up over a half an hour or 45 minutes. But while we can sense temperature differences, but if we've got warm air coming at us for a half an hour, we don't actually care what the temperature is because we feel the warmth. We feel that mean radiant temperature. It's changing our felt sense, right? And now at 7 a.m., I step it up 69 to 70. So over a 2-hour period, I recover 2 degrees. That's just what works for me. It's what made sense. It's what I could program. And I notice it on my utility bill. When people are swinging like 3, 4, 5, 6 degree setbacks in the winter, you're going to see higher bills, period.
A friend of mine has electric strip heaters as backup, but the software called them into action if he asked for more than a 5-degree temperature difference. They would kick in, or if the temperature went below 32 degrees, both of which are completely stupid parameters. And unless you have an installer who points that out and changes those settings, you could be pretty disappointed by your electric bill because this resistance heater is basically a toaster, and it'll cost you.
It'll cost you.
Yeah.
So back to should we, right? Should we raise the temperature 5 degrees? The software engineers, the interpretation would be, well, you're asking for 4 degrees or more, you're asking for all the heat. If you're only asking for 2 degrees, you're asking for some of the heat. I don't know, but that's sort of Mitsubishi and others are similar that way. Sort of a higher grade manufacturers tend to have a little bit more sort of smoother engineering and software design. Mitsubishi, for example, has a delay. If you ask for 2 degrees or 3 degrees, it's going to do what it can to operate on the heat pump only, smoothly, efficiently, to target that, and it's going to say, where am I at? What are you asking for? Where am I at? And am I gaining ground? If I'm gaining ground, I'm not going to change anything. But if it doesn't see enough gaining of ground over 24 minutes, and that 24 minutes is adjustable, you can dial it back to 14 minutes, or you can push it out to 29 minutes. And so if it triggers that, if it hasn't done what you're asking it to do within that time frame, then it'll kick on that backup heat just a little bit for as long as it needs to, and then it'll cut off. As soon as it reaches that point, it cuts off and then maintains the heat pump.
And there's one other aspect that I should mention. Most of the homes here in this regions have vastly oversized gas furnaces, vastly oversized. Mine was like at 150 thousand BTU,
yeah.
And now I'm running a ground source heat pump with 48.
A third.
Yeah, and it totally works.
Yeah.
Speaking of works, some of us have worked hard to feed you after this presentation, so I hope most of you will stay around. And because this is a special day, I brought a bottle of bubbly. If you want to partake, you're invited.
Some good news today. Yeah.
We're a non-partisan organization, so I'll leave it at that. And I'm glad you came here instead of listening to the pundits all night. And with that, I want to thank again Shawn LeMons for this wonderful presentation. Yeah.